there are a couple of really exciting things that have been happening in science and cosmology, which is the study of the universe as a whole, its history, its evolution, what it looks like. And it's all intertwined these days with astronomy, the study of sort of celestial objects, and particle physics, the study of the very smallest things. And we've put a lot of information together and built a really strong case that we have absolutely no idea what 95% of the universe is made of. Now, in order to get to that point, we had to know a whole lot. So it's not as if I'm saying we're complete fools and we don't know what we're doing. It's that we have learned so much about both the universe as a whole and about the nature of the very smallest particles we've ever been able to detect that I can say with pretty strong confidence that when we look out at the universe, this is sort of the cosmic census, a pie chart of what's in the universe today. And 5% of it is normal matter. And I'll explain that in a minute. But the rest, 95%, is in something called dark matter and dark energy. So, next slide, thanks. And it turns out that Einstein himself left us with the blueprint for how to look for these dark substances long before he had any idea that they could even possibly exist. And there's kind of an interesting little story to this. Science sort of seldom proceeds in a nice, smooth line. And this is an example of how things worked out in the end, but they might not have. So in 1912, Einstein was working on his new theory of gravity and how it would be very different from Newton's laws. And he had all these great ideas, and he was making predictions. He was very excited about it, as theorists tend to be, but he needed to have someone test it. So he went to Berlin and talked to one of his colleagues, Erwin Freundlich, and said, I've got this great theory. I need you to go look at this, because I think what my theory predicts is that the presence of some kind of mass, gravity, is going to bend light. And I think we can see this if we use the sun as a mass that's going to sort of put this warp out there, and it's going to bend the light that we see. And he even went so far as to say, so if you've got the sun, and what he was predicting is that you're going to see some little shift in starlight, you can't see that if the sun is there. You need to look for it during an eclipse when the sun's light is blocked and you can see stars that are very close to the disk of the sun. He did write to Mount Wilson Observatory and say, don't you guys have some clever way of sort of looking when the sun is there? And they pretty definitely said no. So he went back and talked to Freundlich and said, can you please go out and try to measure this? So Freundlich got all excited about, here's his chance to contribute to a major revolution in our understanding of space and time. So he gathered a team, and they went out to view the next eclipse that they could see from the best vantage point they could predict. And unfortunately, it was August of 1914, and they headed out to observe this eclipse from the best point of view that they could find, the Crimean Peninsula in Russia. So those of you that know your history know what happened. They got there just in time for the outbreak of World War I. They were captured by, this was a group of German astronomers, they were captured by the Russian army, who confiscated all their equipment, imprisoned the astronomers, and that was the end of it. The eclipse came and went. They could not actually measure it. And it turns out everything ended, as I said, for the best, because about a month later, they sent home the astronomers. I don't actually know what happened to the equipment. There wasn't any record of that. But the problem was, the reason this was a good thing was Einstein hadn't yet finished his theory in 1912 or 1914, and he had it wrong. He was off by a factor of 2 at that point. His work on special relativity let him know that time was going to do some very strange things, and he had time sort of being bent or slowed down by gravity, but he couldn't yet wrap his head around the fact that space itself could be deformed by the presence of some kind of mass. So between August of 1914 and about a year and a half later, Einstein finished his equations, came out with the correct prediction for how much this light should be deflected, got the factor of 2 right, and next slide please. And the next expedition, take 2, went out, and this was Sir Arthur Eddington's famous eclipse expedition of 1919. They had a couple of different teams that went out and actually measured this deflection of starlight as predicted by the theory. The results came in with, uncertainties of about 20%, and I think, and fairly unusually for the time, the results were presented on November 6th to the Royal Academy and the Royal Astronomical Society in London, and the very next day it hit the headlines, announcing a revolution in science, a new theory of the universe, and from that moment on, both science community and the public were very excited about this new theory, and it kind of catapulted Einstein to his position as a genius and very famous. It could have turned out differently if the first eclipse expedition had gone through and it hadn't agreed with theory. Who knows how much more difficult it would have been for everyone to accept this theory. So this was all very exciting, and what Einstein was predicting, if I can have the next slide please. Basically, his new theory of general relativity said that both space and time would be warped by the presence of any kind of massive object. So the usual analogy that we use is if you have a giant rubber sheet and you stretch it out, you have people on all four corners, you put a bowling ball in the middle of it, and it's going to deform that sheet. It's going to cause this dimple in the sheet. You put a baseball over here, it's going to cause a smaller dimple. Now, this is a two-dimensional analogy. It's embedded in 3 dimensions. I think it's almost impossible for all of us with our brains, which are trained on 3 spatial dimensions, to actually picture this. But this gives you an idea. What's happening? The sun is sitting in space, and it's warping space around it. Light is going to travel through space on the shortest lines that it can. But if you've got curves in your space-time, that path is also going to be curved. Can I have the next slide, please? And so this is sort of a cartoon image of if we're on the Earth, and we're looking at the light from a distant star, if the sun is sitting right between us and the distant star, the actual position of the star is shown there. And as the light from the star travels close to the sun, it's going to be bent. Now, this is extremely exaggerated, of course, but what we will see is that the apparent position of the star is shifted. And this is what Eddington measured. They had about a dozen stars, and they could see that they all shifted outward in exactly the way that you would predict from general relativity. And basically what the sun is doing here, it's acting as a giant cosmic lens. It's bending the light from a distant object in exactly the way a lens made of plastic or glass will do. Can I have the next one, please? And it's interesting that Einstein did some calculations predicting that there would be this bending of light. Back in, I've got a notebook. These notebook pages are from 1936, but he did it in 1912 for the first time and actually calculated that you might get a double image of a star, for example, and exactly what the deflection would be modulo that pesky factor of 2. But he redid it in 1936 and submitted it to a scientific journal, and it was called, in this notebook, it's a note to Herr Mandel. Herr Mandel was an engineer who kept, as what I've been able to read in the historical journals, kept sort of bugging Einstein, saying, could you publish this? Could you publish this really cool stuff? And Einstein's response was, can I have the next slide, please? I think I put that up here. To write this paper, and it was called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. That is, a star is going to act like a lens out in space. And he calculated and published the lensing of a distant star, light from a distant star by a closer star like the sun, or any star that's out in the galaxy. The production of double images, the fact that you could get a ring of light, and those of you who have seen the ring of light, this is what I'm talking about, that you can somehow bend light with a lens to make a ring. And he made a note in there saying, it's a most curious effect. Of course, there is no hope of observing this phenomenon directly, and he's talking about the rings or the double images. And in the letter to the editor of Science when he submitted it, he said, thank you for your help with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy. So he's doing this to be a nice guy. And can I have the next slide? And actually, gravitational lensing, which is what we call it, and what I've dubbed Einstein's telescope in this book, is now the most powerful tool that we have for searching the universe for dark matter and dark energy. I don't need anything to shine light. I just need it to warp space-time, and then I can actually look for it.